Okie doke. Now, does anybody have any specific questions? I know we're talking about chapter 6 here this session. Anybody in reviewing chapter 6 run into anything that was puzzling? I think that chapter 6 is actually fairly intuitive, I feel anyway. So hopefully what I'll do is I'll jump in and begin reviewing the end of the chapter quiz. And then if anybody has any issues or questions as we're going through this, just jump on and let me know. It's always better if we're doing a conversation. Okie doke. So anybody just chime right in. A client wishes to increase the power output of their 5-year-old array. Which of the following options would be the best option, barring unusual circumstances? Add more panels, add an active tracking system, replace all of the panels, or add batteries?
Add additional panels.
Yeah, and this is one of the reasons why options like microinverters are very helpful, because you can add 1 or 2 or 3. You know, hopefully you're not going to have to put in all new panels. But with some of the old string inverters, of course, each string had to be balanced and matched. So, you know, if you had to, you might have to replace everything in order for everything to be balanced, because they all operate at the lowest common denominator. So, but a better solution, just add them as you need them. Okay, when adjusting the orientation of a panel east to west, this affects its azimuth, altitude, declination, or resistance.
I'll go with azimuth.
Azimuth, right. East to west is the azimuth. So as it's facing to the east, you know, it transitions. There are tracking systems. So for instance, they might be facing east. As the day goes, they'll turn like that. Most of the tracking systems that we see that deal with azimuth are usually going to be facing north. They're going to be facing north-south, but they are all on a arm, like a rotating arm. So in the morning, the whole arm sort of turns so it's facing east. And then throughout the day, it pivots so that at noon, all the panels are facing straight up. And then the whole arm turns so that in the evening, they're facing west. Then they usually reset themselves to level overnight because of wind loading and things like that. So if there's a lot of wind, they just sort of sail over top of it. Utilities use these a lot. And one of the advantages, aside from they're getting more power because they're tracking with the sun, is they're able to dump off any snow that might accumulate on the panel throughout the day, you know, so they're turning, so you don't have to go out there and do any kind of maintenance. But of course they are a mechanical system. So because there are motors and things turning, there's going to be maintenance that having a fixed array, you don't have to worry about that. So most homeowners would much prefer to just have a fixed array because of the maintenance issue. If you need more production, well, then throw on a few more panels. Determining restrictions on the height of a building adjacent to the property where the array is mounted might be an example of hazard assessment, building integrated PV, commissioning the system, or future proofing.
Future proofing.
Yep, I would say future proofing in this case. And part of the reason for that is, let's say right now I'm here at Zane State campus. Let's say we decide we want to put a solar array in the field next to this building without realizing that there are plans for a 5-story building to come in the lot right next to it. So we put in a solar array and then the sun is blocked later by another building that comes in. So you might want to determine just what are the height restrictions for buildings in the surrounding area. So that could be an issue. Again, normally in residential, that's not a big issue, but it could be with commercial systems for sure. Which of the following would be useful in determining if a specific site has enough sunlight to support a PV system?
solar insolation map.
Yeah, the insulation map, this is a tool that we used quite a lot, but anymore we just use PV watts because these insulation maps that told you how much sunlight was in different areas were notoriously poorly done. So with the PV watts, you can really drill down to get specific information uh, about a specific zip code or weather station or whatever. So solar insolation maps have pretty much gone the way of DOS. You know, I mean, it's really just, it's superseded by PV watts. An array facing solar west will very likely produce 20% less, 40% less, 10% more, or 12.53% less energy than would be produced by the same array in the same location facing solar south.
20% less.
Yeah, this is something that surprises most people because we're always saying that the best option is to have your solar array facing south. But really, if you have a building that faces east and west versus north-south, you can put the solar panels so they're facing east and west, and you're only going to have a 20% reduction versus if you're facing it true south. So oftentimes, especially in, let's say, agricultural areas, you might have a barn that faces east-west. You could put those solar panels on that barn, and then you just have to put 20% more panels on in order to get the same amount of production than if the building faced south. So it's not a game changer, especially since solar panels are becoming cheaper and cheaper, whereas most of the other electronic devices would all be the same. So really, it's just the cost of a few more panels. This right here is a declination chart. All right. And what they're saying is using the declination map below, estimate the adjustment to a magnetic compass while siting an array in Denver, Colorado. So I found out I had to tell people where Denver, Colorado is. So here's the red X. So what it's saying is, as you're looking at this declination chart, notice it says 10, 12 degrees east. Well, declination charts are normally manufactured for pilots. So they're always based on north. So we would adjust our compass 11 degrees east when we're facing north, or 11 degrees west when we're facing south. So in solar, because we're always dealing with southern orientation, I always say that if you're west of the Mississippi River runs right here, which is pretty close to 0. So if you're west, adjust it to the west. If you're east, adjust it to the east, based on solar south. Be the opposite based on solar north. So if I were setting up my solar pathfinder, I would set it so it's facing south, and then I'd move it 11 degrees west in order to get a true reading if I were in Denver, Colorado. It can be very significant. If you're up here in Seattle, Washington, you could be almost 20 degrees off south. You know, when you have a compass that's facing south, it's not really south. It could be as much as 20 degrees off. So south is not south and north is not north. Although if you've got a smartphone, which most people do, a cell phone, many of them have GPS settings in their compass apps. So if you're using a compass app on a phone to get your orientation, make sure to see if they're talking about magnetic or GPS based. If it's GPS, then no adjustment's going to be required. If it's magnetic based, then you're going to have to use their declination adjustment. So all that makes sense? Okay. All right, so an array facing west, oops, we already had that, didn't we? That's going to be 20% less. The randomization is giving it to me twice. I guess it liked that question so much. Come on, catch up. All right, which type of mounting system will increase the amount of time a panel directly faces the sun?
Sun tracking.
Yeah, sun tracking. And sun tracking systems can either be single axis tracking. So that could be like tracking on azimuth, like the unit that I was just explaining to you, that faces east in the morning, west in the evening. Or they could be seasonally tracking so that they're more vertical in the winter, less vertical. There are some that you can do manually for small systems where you just pull out a bolt, go and adjust it. So in the summer, you'd lower it down, stick the bolt back in. In the winter, you'd move it up, stick the bolt in. Those are pretty good because they don't have any mechanical maintenance involved. But obviously, if you have more than, say, 10 panels, they can be a real pain. And if it's a roof-mounted system, you usually don't want to adjust the angle other than the pitch of the roof, because aesthetically it looks terrible and it can get some serious wind loading. If the panel is not set parallel to the roof, if it's, say, kicked up, then wind coming from the north could just tear the panel right off the roof. So you don't want to do that. And then there's dual axis tracking, where it usually sits on top of a pole and it can adjust both azimuth and altitude based on the time of day and what day of the year it is. If no bias is introduced to the altitude of a fixed solar panel, the angle will likely be based on
It's the latitude.
Yep, just think Jimmy Buffett, right? Changes in latitude. Yeah, the latitude. So here along I-70, we're right at about 40 degrees north latitude. So if you think about that, then the perfect angle, as far as the sun would be concerned, would be a 40-degree pitch, because on the autumnal equinox and the vernal equinox, the spring equinox, you would be at a direct 90-degree angle to that panel. So in the wintertime, the sun would be lower on the horizon, and in the summer, it'd be higher off the horizon. But on average, it would match the latitude. So you would think that would be the ideal orientation for your solar panel, but it's not, because the days are longer in the summer and shorter in the winter. And also we tend to have more sunlight, more clear days in the summer. So you would typically have a summer bias to your pitch. So even though on average it's 40 degrees, because the days are not uniform in length and sunshine is not distributed uniformly, it's biased to the summer, you would tend to lower the panel's angle by 15 degrees, which is referred to as a summer bias. That would produce the most power over the course of the year in an environment like ours. And that environment like ours, where summertime has more sunlight, days are longer, is the norm. There may be situations like in monsoon situations where it rains all summer long and it's dry and clear in the winter, where a winter bias might be advantageous. But most places it's going to be a summer bias. Okay, when using the sun chart below, determine the optimal angle. So this is just giving you a little bit of use. So on August 20th at 10 a.m., so we would look through this, and this is the same kind of thing you'll find in a solar pathfinder. So we find August 20th right around here, 10 a.m. right around here. And if we extract that, it's 45 degrees off the horizon or altitude, and it would be around 135 degrees azimuth, whereas solar south is considered 180. Solar north would be 0. So this would be how you would read that. So the answer here would be 45 and 135. So it just gives you a little bit of practice at how you read these things. And these really come into play only if you're going to have to create a sun tracking system or if you're using the Solar Pathfinder for shading. That's really where these sun charts come into effect. When adjusting the orientation of a solar panel up and down in relation to the horizon, this adjustment affects its azimuth, altitude, declination, or resistance.
Declination.
Declination?
Altitude.
Altitude? I'll go with altitude. Declination is for magnetic, your adjustment off of magnetic south. Altitude is what we refer to as the height off the horizon, or basically the angle of the array. So altitude is going to affect its angle, pitch, and azimuth's going to affect its orientation, east-west orientation. Most PV arrays utilize what kind of cooling system? Yep, passive air. This is the reason why we locate our solar panels like 4 to 9 inches off the deck of the roof, because we need to have some way for the air to move and to dissipate, because solar panels are usually about 20% efficient. So the sunlight's rays, 20% of that is converted into electricity. Well, the other 80% is going to be converted into heat. Well, that heat has to dissipate somehow. And so, like, I ran into a situation at church where they had put flashing around the perimeter of the array in order to keep squirrels from getting up in there underneath the array and chewing on wires and the like, or building nests. Well, what they had done effectively is built a little solar cooker up on the roof, trapping all of the heat that was going to be generated, not allowing it to dissipate. So they were getting temperatures, 200, 220 degrees under that array. Well, that's going to melt your shingles. It's going to cause the electronics to do bad things. The wiring, you're going to have higher voltage drop, less conductivity. So it causes lots of problems. So if you want to protect yourselves against squirrels, which are a big deal, that's a big problem, they make like a mesh screen squirrel guard, which keeps the squirrels out but allows the air to travel through. So don't try a do-it-yourselfer with flashing, because that's not going to be the right solution. There are some experiments with cooling with water. That's a nice option, where you could run streams of water over the panels or in the panels, and then use the heat to heat the water, as a secondary hot water source. Those are interesting, but again, now you've got water and pumping, and water and electricity sometimes have a difficult relationship. So you'd want to make sure that everything is properly insulated and sealed. When evaluating a roof for possible PV array, which is not a consideration? The age of the shingles, structural condition of the rafter, the pitch of the roof, or its demarcation point?
Demarcation point.
Yeah, the demarcation point. Obviously, the age of the shingles, if you're going to need to replace the shingles, you should do that before you put up a solar array, or at the same time, even better. Structural condition of the rafters. Often with a building in the city, they're going to require that you have a structural engineering inspection of the building, just to make sure that all of this can support a solar array. The weight of the solar array is not the problem. The dead weight or the dead load. Really, a solar array only weighs about the same amount as a second layer of shingles. And most homes, you can put a second layer of shingles on without, removing the first layer. That's the dead weight, the shipping weight. But the live weight, which is the wind loading, like the amount of power or force that's pushed down or pulled up from the wind passing over, can be significant. So for instance, the dead weight is usually going to be 2 or 3 pounds per square foot, but the wind loading can be 50 or 60 pounds per square foot. So that can be significant. So you want to make sure your structure of the roof will handle it. I usually tell people that if you feel uncomfortable walking on the roof, you should have an engineer come and look at it. Because obviously your human weight is going to be more than 50 pounds per square foot. But some cities require that it be inspected regardless. A demarcation point is just where one person's responsibility begins and the other person's ends. So in an electrical system, that's going to be your meter, usually is the demarcation point. The utility's responsibility ends at that point. Your responsibility begins. So if you have to replace wire or whatever, that's the demarcation point. The winter bias of an array is?
Latitude plus 15.
Yeah, latitude plus 15 degrees. So what we're saying there is, if you can see my hand here, let's say that that is 40 degrees here. Well, a winter bias would be 40 degrees plus 15, so it'd be more vertical. A summer bias would be latitude minus 15 degrees, so it'd be more horizontal. So it would capture more of the sunlight in the summer where the sun is higher off the horizon. In the winter, it would be capture more when it's lower in the horizon. And a lot of times these things come into play, how you want to orient your panel angle-wise. Let's say you have a standalone system. You know, because a grid-tied system, it almost doesn't matter. As long as you're truing up your system on an annual basis, you usually want to just maximize production over the course of the year. So that's usually going to be about a summer bias. But if you've got a standalone system where there's no grid connected, then you're going to want to match production with consumption as best as possible. And it may be that you're consuming more energy in the winter than you are in the summer. Let's say you're an agricultural facility and you're heating water. That's a big thing for us in our farm. So we use a lot more energy in the winter than we do in the summer because we don't have air conditioning, we don't have any of that, but we have heaters for the water. So we might want to set our angle higher, steeper, a winter bias, so that we're maximizing production when we're using the power. And that can get fairly complicated as to how to figure all that out. It's a little beyond the scope of this class, but it's a concept that's important to understand. Why would you pick winter bias over summer bias?
So quick question on that, Jay.
Sure.
Can you use the PV watts, simulate that by adjusting the angle within the calculations within the inputs?
Yes, exactly.
Okay.
Yeah, it's very, very quick, very easy. And that's one of the beauties of PV watts is it lets you do that.
Okay, thanks.
But did you say, you also said on a rooftop insulation that you don't have to worry about that? You just follow the pitch of the roof, right?
Yeah, that's correct. So if you're doing it on a rooftop situation, you're going to get what you get. You know, if the angle of the roof is 28 degrees, that's going to be the angle of your array. So you're just going to have to deal with that. But if you're doing a ground mounted system, then you can usually adjust the pitch of the array. Okay, when placing an array on a roof, which of the following should be considered? The live weight, the dead weight, the condition of the rafters, or all of the above?
All of it. All
Yep.
above.
Everything. Oops. Yeah. All of the above is going to be important. A two-dimensional diagram representing the tracking of the sun over an entire year for a given latitude is referred to as?
Sun chart.
Yeah, that's the thing that we looked at just a few minutes ago. And that's something that's in the Solar Pathfinder unit. And when you use the Solar Pathfinder unit, you're going to get a whole stack of these sun charts, and they're all for different latitudes. So you can pick whichever one, wherever your location is, put it in the unit, and then you do your shading analysis that way. When placing the balance of systems on a PV system, ensure that they're facing as close to solar south as possible. All cabinets and cases are rated for interior conditions. They do not contain any overcurrent protection or none of the above.
None of the above.
Yeah, because when you're talking about balance of systems, like your DC disconnects, your AC disconnects, combiner boxes, things of that nature, you want to keep them in the shade as much as possible. So the ideal location would be to have them facing solar north, so that that's going to be in the shade all the time. Because just like sunlight and heat affects the conductivity or the ampacity rating of wire, it also affects the ampacity rating of breakers, fuses, the boxes, all of that. So if you had let's say you have a disconnect that's got a breaker, a circuit breaker in it, and it's facing solar south. Well, if let's say that there's a 20 amp disconnect or breaker in there, and you start to find that on a hot August day, suddenly the breaker trips, and you keep trying to troubleshoot it to find out why. Well, it tripped because the ampacity, the ability of that breaker to handle amps has been adjusted because of the heat. So it's designed to trip when the ampacity exceeds 20, but it may be tripping when the ampacity exceeds, say, 10 or 15, just because it's gotten very, very hot. So you're going to get some nuisance tripping. And you can't adjust for that like you might with wire by putting in bigger wire, because you don't want to put a 40 amp breaker in when you really need a 20 amp breaker. So the solution there is don't face it in the sun, or if you have to, put some sort of shading, a little doghouse over it or whatever, something to shade it so it's not getting direct sunlight. So that'll be your best. Now, if the thing is outside, then it's got to be rated for exterior conditions. And many, many, many of these BOS, balance of systems, they have fuses, they have breakers. So yeah, overcurrent. When placing several rows of a ground-mounted panel in order to avoid inter-row shading, mount the panels using landscape. Make sure that each one is 9 feet apart. Adjust the azimuth to not less than 15 degrees off true south, or none of the above.
None of the above.
Yeah, because the right answer is going to be dependent on your latitude. So for instance, here, if I've got, what we're talking about is, let's say I've got a solar array, and let's say this over here is south. And I've got one array here, and then I've got a second array back behind it, which is fairly common. Try and give you a little 3-dimension here. All right, so what's going to happen is this array is going to cast a shadow. And you don't want that shadow covering part of the array behind it. So typically you're going to find it's like a 1-to-3 ratio or a 1-to-4 ratio, depending on what your latitude is. If memory serves, here in around 40 degrees, I think it's 1-to-3. So if you've got 6 feet from here to here, so if this is 6 feet, then you're going to want to go back 18 feet in order to avoid that shading. If you're further north, let's say you're in the Upper Peninsula of Michigan, it might be a 1-to-4. So if you're 6 feet, then you'd have to go back 24 feet in order to avoid that inner row shading. So it can require quite a lot of space. Now, there are some more complicated ways of figuring that out, but that ratio works pretty nicely. And there's really no reason to go through all of the calculations. If you stick with the 1 to 3, you're going to be fine, 1 to 4, depending on your latitude. Which of the following is an example of dead weight of a PV system? The weight of an installer walking, pressure from wind flowing over the array, the shipping weight of the racks and panels, or the weight of the shingles and the decking of the roof?
Shingles and decking.
Shingles and decking?
Wait.
It's actually going to be the weight of the panels. This is the dead weight of the roof, but the question was, what's the dead weight of the PV system? So the dead weight is just going to be the shipping weight of the racking, the panels, the electronics, whatever you're putting up there on the roof. So that's the dead weight. The live weight, typically we're talking about installers walking around, wind flow. In California, especially seismic tremors will cause a weight issue on your panels. So you've got to factor for that as well. One of the nice things about the panel manufacturers in today's environment is if you're going to be installing a system like on a roof or even a ground mounted system, they're going to ask you for your zip code as part of that design. They usually have online design tools. And in fact, I think in one of the upcoming chapters, you'll walk through this. But when you put in the zip code, it will automatically put in your wind load factor, your seismic factor, your snow loading factor, all of these other issues that you would have to calculate. They'll build that into your design. So if you're in a high snow environment or a high wind environment, based on your zip code, it will design your system to withstand those. So it might narrow some of the supports, might require more supports, that kind of stuff. Which is preferred, landscape or portrait orientation?
It's determined by the racking system.
Yeah, so what we're talking about there is basically when, you know, if you think about landscape or portrait, normally like this cell phone, this would be portrait orientation and this would be landscape orientation. So just how they're mounted onto the rack is largely due to the racking design. And different racking systems will have them placed on there differently. Peak sun hours is a measurement of the location's declination, azimuth, latitude, or insolation.
Insulation.
Azimuth.
Peak sunlight is going to be insolation. And insolation is a word that just basically is an amalgam. There's a term for that, but incoming solar radiation. So what we're doing is taking irradiance, which is measured in watts per square meter. So under standard test conditions, we have about 1,000 watts per square meter, and we're converting that to hours of peak sunlight. So we're saying for this particular location, how many hours of 1,000 watt per square meter units do we have over the course of a typical day? And that's referred to as insolation. So when you look up on PV Watts and it says that in Central Ohio, you have 4.32 hours of insolation, they're not saying that the sun only shines for 4.32 hours and the rest it's darkness. They're saying that over the course of the day, you have 4,320 watt hours of irradiance hitting a square meter section of land. So in the early morning, it's going to be less and diffused. Noon, it's going to be stronger. Evening, it's going to be less. But when you take it all and measure it all together on average, it's going to be 4.32 hours of 1,000 watt per square meter sunlight. And that's going to be very helpful when we're doing our calculations to figure out, what size array we need. So that's what insolation. And every time I write a textbook, my wife Annie always tries to correct the spelling on the word insulation because she thinks it should be insulation, with a U instead of an O. Keep saying, nope, that's how it's spelled. So, all right, so we got all of the answers right. Were there any questions in the labs or anything like that in chapter 6?
So I got stuck on the Pathfinder lab.
Okay. Yeah, let me see. Let me pull this
Some of
up.
it I was reading, but
Yeah, I'll bring that up just so we can see what we're talking about here.
Do people still use those, Jay? The Pathfinders?
Oh, yeah, all the time. Because they're relatively inexpensive. If you wanted to use like a Solmetric or something like that, you might pay several $1,000s. Whereas something like this, you can get one online for about, $100, a used one. So this would be the sun chart that's part of it. And this, for instance, is showing it's between 37 and 43 degrees north latitude. And then this is showing the sun's locations throughout the year. And then this would be time of day. Be sure you don't confuse time of day with time of day. This is solar time. This would be solar noon, which is when the sun is directly overhead. And that will be different at different locations. I try and reinforce this by telling people the sun doesn't know when you switch from daylight savings time to standard time. So, and it varies depending on where you are in the time zone. So solar noon might be like 1:30 in the afternoon. It really depends. You can look that up online to find out what it is in your location. So this is what you're seeing. And what we've done is marked where the shading is. So in this particular one, when we took the reading, we found that there was a tree shading here, a pole that was here, say another tree over here. So when you're reading this, it'll say, okay, well, in June and July, pretty much it's unshaded all day long from dawn to dusk. As we move up into August, April, yeah, in the early morning, it's going to be shaded by this tree, really pretty much all the way from March through December. And the pole here only affects us a little bit in the mid-afternoon, but only in the winter time. And this over here affects us. So by looking at it, you can get a visual of where the array is going to be shaded when, 24 hours a day, 7 days a week. Okay, so any day of the year, you can go out and take this reading and it's going to tell you where the shading is going to be occurring. Okay, now these little numbers here, like the 1, 2, 5, 6, 7s, these kind of things, what that's telling you is the sunlight that comes during this time of day, like right around noon, is giving it an 8 or a 7 rating. It's more valuable to you than the sunlight that comes in the early morning, where it has a 1 or a 2, because in the morning, there's not as much energy in the sunlight. It's coming in at an angle. So if you add up these numbers all the way across, it should add up to 100%. So each of these lines will add up to 100%. And it's just saying, okay, if we were to add up 3, 2, and 1, this time of year, we're going to lose 6% of the energy from the sun during the day because of the shading of this tree. And this time of year, during March, we're going to lose, in this case, 8% here. And if we follow it all the way over, another, say, 4% here. So we're going to lose about 12% in March because of the early morning and late afternoon shading. So that's what those numbers are telling you. Oftentimes, if you're getting a
As long as
grant,
we're good.
so if you're getting a grant, you're going to have to demonstrate that the site that you've selected will harvest a certain percentage of the available energy. The reason for that is because these grants don't want to be given out. I mean, there's a limited number available, and they don't want to give them to people who are putting solar arrays in lousy locations. So they're going to require that you are harvesting a significant amount. Often it might be 80% of the available sunlight, you know, so there's a whole total solar resource availability kind of formula that you have to go through. And that has to do with how did you orient it, what's the angle, and what's the shading issues. And you've got to be making sure that you're harvesting X percentage of the available sunlight.
Right. So my question was about how do you handle the partially shaded, like, you know, you look up in February, December, January, it's like halfway through for that. So do you have to subtract maybe another 2% from that?
Yeah, you're talking about, you broke up a little bit, but let's say you're talking about January here. And you've got a little bit in here in this 4. So you're just going to guess. I'd say maybe 1% more there. And it seems to me is in this thing, I used to have this set up where I had exact numbers. And if you guessed wrong, you know, in your rounding or whatever, it gave you like your answer was wrong. I tried to give it a little bit more flexibility. Was that what you were running into? Is that you would answer
Yeah,
what
and
made sense and it was telling you you were wrong?
I was just outside the range for some of them, and I think it's because I was using the whole numbers instead of the partials.
Yeah, like here you'd say 2 and 3, they're completely, but this one's only a part of 4. So I'd maybe throw in 1. If it were halfway, I'd throw in 2. So yeah, just pick a part of that number. Does that make sense?
Yes, and then so in that same way, I guess with the pole, you end up not subtracting really any more than 1.
Yeah, yeah. That's all
For
I
that,
put
right?
in is like 1. Yep. Now in the real world, you're gonna, you know, end up with a number and you're gonna stick with it. With this, where it's trying to match an answer, you might have to try it a couple of times, see which one I was going with. There's really no right or wrong on this. I just wanted you to get practice at it. Well, I guess there is a right and wrong. I mean, you could be really wrong, but if you're within a little bit, you know, the margins are there. All right, anything
Right,
else?
and I was just like a little bit farther outside.
Yeah, yeah. Yeah, this can get pretty complicated when you're dealing with grants, and it can be significant as far as production. In fact, I was talking to some installers in Illinois, and they have a program in Illinois where you remember the idea of RECs, where if you were to sell your SRECs, you will receive money back over the course of your production. Let's say that you sell your SRECs for $100 a rec. So for every megawatt hour of production, you're going to get $100 back. And that's an incentive program put in place by the state. Well, the state of Illinois has come up with a program where as soon as you install your solar array, they will pay you 10 years worth of SRECs up front. So they're going to go and estimate the production. So you might spend, say, $20,000 on a solar array, and then you might get a check back for $6,000 for your 10 years of SRECs. So it's an incentive that's being essentially underwritten by the state. So they're paying you up front, and then they're collecting the SRECs over the next 10 years, paying back the state. So it's a real big incentive. And one of the issues around that is that you must be certified And the ETA certification qualifies for that if you're going to qualify for that program and you're installing the system. But if you are an installer, the other kicker is your production estimates better be accurate, because the state is prepaying based on your production estimates. So they do require you to post a bond. And if it turns out production was less than what you estimated, you as the installer have to pay back the state for that difference. So that can be significant. So that's going to really incentivize installers in Illinois to underestimate how much their arrays are producing, so that they don't get hit by some sort of bill in 10 years because their system was not producing the way it should have. So this stuff comes into play often in the real world. Okay, any additional questions on that? Or on anything? Life, the universe, and everything? Okay, all right, well, hearing none, let's adjourn, and then we'll begin on chapter 7 for the Thursday meeting. And chapter 7 is the mother of all chapters, so you guys are going to really enjoy getting into the nitty-gritty. I think chapter 7 is where the design elements all come together, and all this foundational stuff that we've been talking to comes into play. So we're going to spend a couple of meetings on chapter 7. So it's a big task. So allocate plenty of time for it.
Great.
All right. So I'll see you guys on Thursday.
Thank you.
Thanks, Jay.
All right. Take care.